I will today be talking about mathematics. Well, yeah. And the part of mathematics I'd like to talk about today is vectors. They are interesting, and they, as much of other things I've been through, they have power in describing the world, and they are good for that sort of thing. And I'm gonna start with a really simple vector. Actually, I'm not gonna start with a vector. I'm gonna start with a number. I'd like you to consider a number. Let's consider the number 1. It's a very nice number. And I would like to draw something. I'd like to draw this axis. It's just one axis. It's the axis of all real numbers. I have to remember days now. It must the day before yesterday, Saturday, I believe. I went through some notation, and I still haven't fixed this, but there is an R, and if we just do this, this very clearly means the real numbers. This is all the real numbers, and I'm gonna draw the number 0 should be in the middle. That makes sense. There's infinitely many numbers on one side and infinitely on the other side. Yeah, but up here is the positive numbers. Yeah. Now there are zeros in the middle, and at some point there is 1, and at around the mirrored to 1 is -1, of course. That's the way it has to be. -1, and then after 1 comes 2 and 3 and so on. And in between there's of course all there's some rational. There's not all the rational numbers, but there's some rational numbers. There's not any whole numbers, but and there's some irrational numbers as well. And now I'd like to consider the number 1 as not as a set with one thing in it. I like to consider it a line. A line, and how long is it going to be? You guessed it, it's going to be 1 long, and it's just going to go in this direction. So it's going to start in 0, and it goes out to 1. Yeah. Well, actually, it doesn't matter if it starts in 0 and ends in 1. What matters is the length, and only the length. Well, no, not only the length. The orientation is important, and the length. That's the only two things. It could go from 0 to 1, minus 1 to 0, pi to 4.14159, and etc. It's the length. It has a length of 1, and yeah, and in that sense, I can think of it as and you can think of it, and I'd like to invite you to think of it as a vector with length 1. Of course, we could do this with another number. We could do this with the number 2. We could make a vector that has length 2, so it would go from 0 to 2, or from -1 to 1. It's just, yeah. This is a new way in which to see the real numbers. It could be the number pi. It would then go from 0 to pi, but it could start anywhere and could end anywhere. It doesn't matter. These are one-dimensional vectors. And why do I call them one-dimensional? Well, it's because there's only one thing describing the length, describing the vector. It starts in a point. Yeah, you can see my cursor. That's good. It starts in a point and continues to another point, and it goes from left to right. Well, it doesn't just go from left to right. The positive vectors, the positive numbers, will go from left to right on this axis, since you can tell that it has the negative numbers over here and the positive numbers over here. So it goes from the negative towards the positive numbers. A vector with a one-dimensional vector of length 2 could for instance go from -4 to -2. it's another way of thinking about vectors, and it makes sense. For instance, if you have a big negative number and then adds a smaller positive number, you don't get past 0. For instance, it's still negative. You could do this with a negative number as well. It would then just go the other way. It's still a vector, it still has the given length. For instance, I could do -1, and then it just go from 0 to -1, or from 1 to 0. It subtracts 1. Or if I had chosen 17 instead, it would be 17. A negative number is just a vector in the other direction. It still has a length, and it's still one-dimensional because it's only one number to describe it. That one number describes the orientation, in which way it points, and how far it points. That's the two things that are important. If I took, let's take the vector 17. So we have a vector, which is that it is a vector, is marked with this little arrow that I hope you can see, and and it's called V, and it's 17. So the number 17 I now consider a vector called V. And if I then took another vector, called it something different, U for instance, and took the vector -3, nice vector. So 17, instead of viewing it as a single number, I'd like to view it as the line from 0 out to 17. But it's just a piece of line, and then that goes from somewhere here to there, and -3 is then from here and then a bit that way up on the line here. It would be somewhere around here. And we could then add these two together. So the vector 17. So what I mean when I say add them together is go out the first and then go out the second. I've picked some bad numbers for this representation, so I'll just make a new drawing. Well, I'll make a new, and this will be scaled down. So this 17 vector I would like to paint something like this, and the -3 vector I'd like to paint. Oh, there's a little extra dot there. These are not to scale, but it's just to see sort of what's going on. So what I mean is to first go out when I mean by adding them is first I take this one vector, and then I decide to start here, and then I go out this direction, and then from here I'd like to go out the second vector, go this vector. So that means going a little bit back. That's the way of, at least to me, that's the nicest way of thinking about how to add vectors together. You start in a point, doesn't matter where it is, could be 0. It's very nice to start at 0. Start in a point, go out one vector, and then goes in the direction of the other vector. So this is quite boring in one dimension, but in multi-dimensional spaces, it's much more fun, of course. Well, as you might have guessed at this point, these two vectors added together will give me the number, or the vector, 14. Because it'll go out here, and then it'll go a little bit back to around there. This may not exactly be the length of this vector, but it's going to be close enough. So it's not. I just want it a bit closer. Yeah. So this slightly shorter vector, which is placed on top of the longer vector, is the result. It's the resulting vector. In physics, it could be the resulting force of some objects. For instance, if there's someone, this is physics. I'm not that strong in it, but it's, I believe, the way around. If there's a big person pushing with a force of 17 and a smaller person pushing with a force of 3, the resulting force is 14. That's that's how physicists might think of it, and it's a nice way of thinking. It's a nice way of thinking about it. Yeah, if this had been a positive vector and it had gone in this direction, let's say for this, it could have been +3 or +4 or anything at all. It would have gone to here. We would have taken the first vector up to here and then added the second vector, and the resulting vector would have been from here to somewhere out here, depending on how long I made that. And then there's another thing we can do, and this requires something difficult, and if it's not easily understandable, it might get better in 2 dimensions, which you wouldn't think that, but it actually might. We can scale these up. If we have a vector of a certain length, let's say we have a vector with a length of 2, and then I want not a vector but a number. And this is, of course it's the same. It's actually the same thing. I want to take a vector v, which is the number 2, and I want to take the number 5. So there's 2 numbers in play. One I consider a vector, the other one I just consider a number, a multiplier. And what I then want to do is take the vector 2 and multiply it with 5. So if this was somewhat to scale with the drawing above, no, this is not quite far enough. Something like this is better. Yeah. So this is the vector. This is the vector 2. Oops. There we are. Then I want to multiply it with the number 5, and of course it would then be 10 long, because what the 5 does is that it makes it longer. And oh, I guess I could. Yeah, now I am on a computer, so I can just take 5 of these arrows, put them in a line. I should really show this again. So this vector is my starting vector, the vector of the number 2, and then I multiply it with 5, I scale it up with the number 5, and I get 5 vectors in a row. 1, 2, 3, 4, 5. Yeah, and the resulting vector is then the vector that goes from here all the way there. So I will paint this a second time, because it might be difficult to see, but it's already painted here. But I'll just do it again here. Yeah, this is the resulting vector, and this fits into our normal notion of how things work, because this vector will then be 10 long, and that's what we normally perceive. Yeah, you can tell from looking up there. If I counted this, I know that each one of these is 2, so that'd be 1. I mean, it's pretty clear that this makes a vector which is 10 long, and that's very nice, because that fits into our normal terms of 5 times 10 is 10. Hopefully it is. And so, well, it is. And what I like, what's nice about this, and what makes the mathematics consistent, is that these 2 different ways, very different ways of thinking about the numbers, makes the same as the normal way of thinking about the numbers. And I find this generally amazing in mathematics. In general, it's very nice that mathematics has the ability to think of the same things in different contexts. That we can think of the numbers in both it's a number context, but we could also think about it in a vector context, and we can add things, multiply things, and I will not go through division, because division is the same as multiplying with the vector which is a 5th long. If I wanted to multiply with if I wanted to divide with 5, yeah. And really, we should now get on. I will now get on with the vectors in 2 dimensions, because yeah, this is just a different way of viewing something we already know, and that's not too terribly interesting. Yeah. So I'd like another dimension. Where shall I draw it? I shall draw it orthogonal to the first dimension. If not, it doesn't make, well, yeah, that's gonna be the nicest, isn't it? And this is not. I'd like to move that 0. I can't get to do that. Oh well. This is so on the new line. This in here is 0 as well, and somewhere up here, and somewhere down here are the numbers 1 and -1. Yes. And well, this is just a system of coordinates, isn't it? I hope you've seen this before. Probably have. And now a vector is not just a number. Now a vector has 2 dimensions. And I'd like to consider the same vector as we did just then. The vector which goes from here out here. Well, it doesn't really make sense to draw it now that I think about it, but you know, it's back there. I could no, I don't want. I will not do it in a different color. So the vector we had just before can be viewed as a 2-dimensional vector as well. We just add a 0 down in the other row. Oh yeah, and I guess I'll not just quickly go through what this notation means. It this means 2 in one direction and 0 in the other direction. So there's two axes, and they are orthogonal to each other. Well. So if I wanted to draw an arrow, which a vector is essentially an arrow, on a piece of paper, it would have to be 2-dimensional. Yeah. If I wanted to draw it on a piece of paper, I can describe it with 2 dimensions, because I need 2 numbers to tell about my vector. Yeah, and I'd like no, not you. Because I can split my vector into 2 vectors. This, you may think that this is overdoing it, but it's actually turns out to be really nice. And because this 2-dimensional vector can be described as 2 1-dimensional vectors, and I guess that's what really makes it 2-dimensional. That this black vector cannot be expressed in 1 dimension. It sort of needs another dimension to it. It's deeper, I guess. So what we do is that we describe it as a horizontal vector and a vertical vector. I believe I'm using those words correctly. If not, it's the other way around. Yeah, and this vector is 1-dimensional. It goes in the direction of the x-axis, so it's parallel to the x-axis, and that means that it's yeah, so it's just a number from the x-axis really, and the other vector is then and at least up is not difficult to find. It's the same way for you and me, which is nice. The vector up is the direction in the the up vector can be described as a 1-dimensional vector that goes in the direction of the y-axis. Normally I've completely neglected to say this, but probably you know that these would be called the x and y axes. This one, I don't really know. It looks like it could be. It's not quite 2, is it though? I would then maybe this black vector I'd call u. And call it. It's not quite 2, is it? So I'll stick with 1.6. I believe this is something like that. Maybe it's shorter. Let me know what you think. Yeah, and the up one is 1.2 maybe. This vector is this vector. Well, it's supposed to be anyway. Maybe not completely to scale, but hopefully you get the point anyway. Yeah, you can, and these are each, well, they are numbers, but they are all. They can also be seen as one-dimensional vectors. It's just that it's very important to make sure that you know that that one goes in the direction of the x-axis and one goes in the in the direction of the y-axis. That's very important, because if not, you could just add them and it would make a horizontal vector. Yeah, and that would be completely different, of course. Oh well. If we then have this vector, we can add another two-dimensional vector. If, for instance, if I wanted to add this vector to the first vector to the second vector, what I mean by adding is going from starting somewhere, going out in this direction, and then adding this second vector. And then now is the time when I'd like to do this. Not completely thought through, is it though? Oh well, it'll have to do. So I take the vector u and add the vector v, and the resulting vector will go from here to there. So this vector is the resulting one. Now you may have been confused by me drawing them all over the place, but it's because what matters about a vector is its direction and its length. And its direction and its length can be described with these two partial vectors, these two simple vectors that go in the direction of the x-axis and the y-axis. This one can be has a direction and a length, and it can be described as these two vectors added together. And if I want to add two other vectors together, I'll add and I can add, you know, vectors that aren't just the boring ones, but the more interesting ones. And it'll just make a longer vector. And yeah, but the placement of the vector doesn't matter. It's nice when you have, if you have just a number like the number 3 or 17, I believe it was. If I have the number 17, it's nice to think of the vector as going from 0 to 17, because that's, you know, that's the vector. But it might as well go from -1 to 16. It's the same vector. It doesn't matter where it starts out from. Yeah. Now I want to go through something different. No, I just want to say that you can take the negative of a vector. You can, so to speak, multiply it with -1, and that just means to go in the other direction. So, well, I guess that's what we actually went through with the positive numbers. That you have a vector 2, and then you take -2, and it's the same vector, just in the opposite direction. The same is true for this one. The minus this vector would go in the other direction. It'd go down here. Yeah. And if I wanted to not add these two together, but subtract this one, so it'd be let me just think if I've done this wrong. This will give me, yeah, I would have to go out the first vector. This might get confusing, but hopefully you'll follow me. You, instead of, when you have gone out the first vector, the u, you then, instead of going in the direction of the v vector, you go in the opposite direction but the same length, and it would end somewhere around here. So the resulting vector would be something like that, like this. Yeah. This is the I will not bother making tiny arrows in Paint, because that's a pain. Instead, I'll just call this U, and I'll call this V. Yep, it's the right way. And this is U plus V, and this is U minus V. These vectors, these are the vectors you get if you add them together. What you can then do is scale a vector. Again, it's just you take a number and you multiply your vector with this number. So, for instance, if we took I did it just before with the v vector, but considered as a number. Now I'd like to we could, for instance, consider the u vector and scale it up with a number 2, and it'd be twice the length, 10, or it'd be 10 times the length, or minus 10, and it'd be 10 times the length, but in the opposite direction. In the opposite direction, it'll be going somewhere down there. Yeah. Yeah, and that's very nice. The thing we can't do, though, we can't meaningfully multiply two vectors, because what's that going to be? I mean, it's just there's not really a clearly defined way to do it, so it's a little bit, yeah. What we instead can do, because there's another thing we can do, which is sort of funny with vectors, and I have been through this actually already in the second episode, I believe. Is the dot product I could take, and it's written like a multiplication sign, but it's not a multiplication sign. I'd like to take this and yeah. U vector dotted with the v vector, and yeah, and how's this done? I won't go through this in too much detail, but it's just the two top. If I just move this back here, there's U dotted with V. It's the two top ones multiplied together, and plus the two bottom ones multiplied together. So in this case, the result of this would be 3.2. Notice that this is a number. This is not a vector, this is a number. I guess you could view it as a vector, but we don't like to say that. We like to say that this is just a number. So you go from having vectors to having a number, and it's a little bit fiddly. Yeah. Yeah, I said before that the important thing about the vector is its direction and its length, and therefore I'd like to have a way of knowing a vector's length. How long is a vector? How long is vector v? Well, luckily that one's easy, isn't it? It's just 2. It's not a problem. But how long is vector u? It's a little bit difficult, isn't it? How long is this? But luckily there's a guy who wants to help us. Yeah. It's a guy, he's very friendly, and but he's sort of dead, unfortunately. His name is Pythagoras. Yeah. And Pythagoras would like to help us. And why would Pythagoras like to help us? I am using the Pythagorean Theorem, but why am I using it? Well, u can be described as 2 vectors, and you may have noticed this makes a nice triangle, and because it's a right-angled triangle. Goes. Yes, like this, isn't it? Yeah, it is. It makes a right-angled triangle, and we know that in a right-angled triangle, this one squared plus this one squared makes the hypotenuse squared. So I just have to square each of the coordinates and then add them together and take the square root. And my program will calculate this for me. This makes 2. So, wow, that's a really lucky vector I've picked. This vector has the length of 2. That's suspicious. No, but it's true. That's strange. So you could say that by luck, I'm afraid, taken this vector and turned it a little bit. Yeah. Could be something different, of course, as well. If this had been longer, this would have been longer, this would have been longer, and it would have overall been longer. Yeah. We could find the length of u minus v, for instance, if we wanted. Oh yeah, so because this whole minus malarkey, it's very nice to go out one and then go back the other. It's a nice way of thinking about it, and you always remember what it then becomes, but can get a little bit tricky. But what do you actually do for the maths bit? Well, what you do here is you just take the coordinates u minus v, so it's 1.6 over 1.2 minus here we are, 2 over 0, and this makes a vector. Oh yeah, I can do it like this. This is the way to do it in the terms of the coordinates. Yeah. And this makes minus 0.4, I believe, and this makes 1.2. Yeah. So what's the geometrical interpretation of this? Well, we start in the same point. We start in the point where we decided to start. We decided randomly, but it's just we had to choose something, so we just went with this one. We liked it. We have to go minus 0.4 in the direction of the x-axis. That's a little bit backwards. And then we have to go 1.2 in the direction of the y-axis, a little bit up. And we get this vector. So, yeah, you can tell that the algebraic way of thinking about it fits with the geometric way of thinking about it, which is very lucky, because it would have been a bad thing, a bad day if they hadn't been coinciding. If they had given us something different, it would have been not very nice. Yeah, and this vector here, we have a nice new vector with a slightly strange name, but it's a vector, and we can find the length of it. I would write this. I guess I should do some notation as well. No, I'd like all of this. This is not the button I was looking for. You may not see anything, but my screen just did not treat me very nice. I'd write it like this with two norms, with two lines, and it means the norm of the vector. And we would say it in mathematics, the norm of the vector. No, he doesn't want to play. I know how to make him play. Yep, there we are. So I'd like a calculation in between. You forget what you've seen, and notice that this is square root of minus 0.4 squared plus 1.2 squared. And it's the same thing. Good. Yeah. Again with the Pythagorean theorem. And of course, this may not be too clear, but you may notice that it doesn't matter that it goes in the other direction. It's still it doesn't matter that this number is negative, because we square it, and it becomes positive, and then we add them together, and it gives us a length. Yeah, which is nice. That it doesn't. If I took the vector minus 1 point over 0, it would go from here to here, and if let me just we'll just do it. Minus 1 over 0, and the length of this would then be minus 1 squared plus 0 squared, and the square root of that, which would be 1, luckily. Because in our way of thinking, well, this should have length 1. Yeah, and even though it's a negative number, it still gives a positive length. And yeah, that's nice, because it doesn't really make sense to talk about a negative length. It's, at least not in my understanding of the world, it's yeah, what would that be? I mean, it's always a number between 0 and infinite. Well, yeah, between. It could be 0 if it's not really a vector, but it could be a vector of length 1. No, a vector of length 0. Oh yeah. Yeah, and Saturday I talked about complex numbers. They have a real part and an imaginary part. For instance, what would be a nice negative number? Z is, for some reason, mathematicians like to use Z about imaginary numbers. Doesn't make entirely sense. It doesn't make complete sense to me, but I'll stick with it, because that's what everyone else does, which is a terrible argument. But I guess we have to do something, and if we all do the same, it's a little bit easier. I'd like a smaller number here. Yeah, let's do 3. So Z is a complex number. It's 4 plus 3 times the square root of minus 1. Yeah, and actually this can be viewed as a vector. It has 4 as its real part and 3 as its imaginary part. So it would be the vector that goes from somewhere, and 4 in the direction of the x-axis, and 3 in the direction. Well, I'm not showing that, am I? But 4 in the direction of the x-axis and 3 in the direction of the y-axis. If we give these, yeah, I need another tiny bit of notation. I need the real part of Z, the number above, is 4. and the imaginary part of Z is 3. Hopefully you can see why this should be what it is. It's one of the nicer things that doesn't take years and years of understanding. It's just the part that is not multiplied with I and the part that's not multiplied with I, and I'd just like to get that number. So if we call this an x coordinate and this a y coordinate, we could put it into our into our coordinate system of coordinates, and if we call this re and call this im, I could then paint a vector which would look, what shall we say, something like this. And this vector would be the same as the complex number of Z, or they would be equivalent. They would be pretty much the same. Yeah, and you will then maybe notice that the way I added complex numbers is the same as the way I add vectors. I take the real part. If I have two complex numbers, I'll take the real parts and add them together, and the imaginary parts and add them together. I'll take the first coordinate and add them together, and the second coordinate and add them together. And the same for minus. I'll take the first and minus the second, and the second and the first and minus the first, and the second and minus it with the second of the other one. Depending, well, I'm showing it the other way around as what I actually did, but it's just because I'm talking about v minus u, and this is u minus v. But you know, the top ones and the bottom ones, I just put this into the other shape, and it's exactly the same thing I do. This is again where you're free to ask questions, because yeah, I have played around with this stuff for a long while, and I know my way around it. I know my way around it by now. I think, yeah, I would like to say something about orthogonal vectors. Two vectors, well, you know, they are orthogonal if they are like this. Doesn't matter which way. If they're like this, they are orthogonal. But the definition, the proper rigid mathematical definition is not. There's proper mathematical decisions, and it has got to do with this dot product. It's actually, the definition is, if the dot product of two vectors is 0, they are orthogonal. Which is, at first maybe you'd think it as a bit of a stretch, but it turns out to be not that bad. And now I'll do some vectors that I won't draw because it's nice to see them, but it's not always necessary, and sometimes it's much easier not to draw them. For instance, I could take two vectors. Even though I won't draw them to scale, we still need to think about them. I'll take my v from before, and I'll take a new vector, just a random one. Well, not completely random, but somewhat random. 5. So how would this vector look? It'd be this one again. And how would this vector look? Well, it'd go 0 out of the x-axis and 5 up. So it's a bit out. And what you'll probably notice is that these two vectors are orthogonal. At least our normal way of thinking, we would suppose these two to be orthogonal. And let's see if the dot product is actually 0. Well, the dot product would then be the two top ones added with the two bottom ones, all in pairs multiplied. Well, let's see. This makes 0. Yeah, it does. Okay, it fits. Yeah. And I could do, I guess I'd have to make some orthogonal vectors in order for it to be to make 0, but still is. It's well. Oh yeah, I have to. If I did, let's do 5 and 3, and we'd like to dot it with -3 and 5. Yeah, so what I've done here is actually take a vector. This is not to scale at all. It's just to visualize it in some way, and then I've turned it a bit. Yeah, and this dot product, this will make. I'll write it out. It'll make -15, because 5 times -3 is -15, plus 15. Oh, what? That's not 15. Oh, yeah, 0. Let's take a new vector. Oh, yeah, you can see this. You can see this. Good. I want to do a vector. I want to do -4 and 7, and I'd like to dot it with this. God, sorry, my brain is working slightly slow. 7? No, not 7. We just had 7. 14 and 8. Oh, 8. Yeah. So if I had to draw a quick sketch, no, I'll first calculate this, and hopefully I'll have actually picked 2 vectors that are orthogonal. This is interesting, isn't it? For me the most, but still for you as well. -4 multiplied with 14 plus 7. Yes, this is 0. I was scared there for a moment, but yeah, it's 0. And if we just forget that it was 0 for a minute, I'll just do it like this. We can look at them and sort of think, well, -4, that's if I want to start in this point, and then I go 4 back, and then I go 7 up, something like this. And then the other one should go 14 forwards. Oh god, this is going to be slightly big. 14 forwards and 8 up. Something like this. This is clearly not scale, as you can tell. Well, I guess it's more like this-ish. But they look somewhat orthogonal. Yeah, and it makes 0, so by definition they are actually orthogonal. Oh yeah, and this makes sense with I said some time ago that the y-axis and the x-axis are supposed to be orthogonal, and this makes sense, because if we took any vector in the direction of the x-axis and multiplied it with a vector in the y-axis, in the direction of the y-axis, it would be something like this. This is in the direction of the x-axis and the direction of this y-axis, and you can hopefully see that it doesn't matter which numbers I put in to this to the slot of 2 and the slot of 5. It could be a negative number or a crazy decimal number. Doesn't matter, pi or whatever. It would still make 0. So the 2, and therefore I can say that the 2 dimensions show us are orthogonal, which is nice because I'd like them to be. Then, and this is where it gets quite difficult. Oh yeah, there's something about vectors being parallel as well. but I'm not gonna bother with that. No, because there's no really interesting qualities about two parallel vectors. If for instance the vector 2 and the vector no, this vector and the vector 4 for instance, they'd be parallel. The only thing we can say about them is that they are orthogonal to the same things. If we make two vectors pointing in this direction, and then make a third vector in that direction, if it's orthogonal to one and the two are parallel, then it's orthogonal to the other as well. This makes sense, and you can check it with the calculations and do them. Find two random vectors, find another vector which is orthogonal to one of them, and you will find out that it will be orthogonal to the other one as well. It might not seem like it, but it's actually true. It doesn't seem like it to me right now as well. Anyway, so well, then there's well, it doesn't stop here, does it? Because we live in three spatial dimensions. What I mean by that is that if you wanted to position something in space, you need 3 coordinates for it. You can make... I want to say this in a way that makes it understandable. I can have 3 vectors that are each orthogonal to all the others. In 2 dimensions, here on my paper up here, I can make 2 vectors which are orthogonal to each other. I will not bother with the well, I will, because a vector has a direction and a length. I can draw 2 vectors that are orthogonal. But if I draw a third vector, it can't be orthogonal to both of them. It can be orthogonal to one, but it can't in any way, no matter how I turn it, can't be orthogonal to both of them at the same time. This will not be orthogonal to any of them, no matter in which direction it goes. The only vector that will be orthogonal by definition is the 0 vector, the vector that goes nowhere, which is just a point, and that's really boring, and that doesn't matter. So we'll forget about it. The vector I'm talking about, of course, is oops. No, I should really do this at the bottom just to avoid confusion. This vector. By definition, it's orthogonal to everything, because if you take the dot product of this vector and any other 2-dimensional vector, it will make 0. You take this, multiply with something, and add with this, multiplied with something, but it doesn't matter what you multiply with 0, it makes 0. So this will be by definition be orthogonal to everything, but this is a really boring. It's not a real vector, and it's not called a real vector. It's just a 0 vector, and it doesn't matter. This is not it doesn't have any dimension actually. It's a 0-dimensional vector because you don't need any information to describe it. It's just a point. In a 3-dimensional space, however, you can have 3 vectors orthogonal to each other, and this is where it gets really difficult to paint, to draw. However, I shall give it a go, because what I really need to draw is one vector going up, one vector going to the side, and then one vector pointing no, this has to be different. Yeah, this has to be the other way around. Sorry, this is a necessary mathematical detail. Can I flip this? No. Yep. can actually flip this. This is an unnecessary mathematical detail, but this is the better way. This might be the x-axis. This could no. This could be the x-axis. This could be the y-axis, and then there'd be an axis pointing towards you. Well, I guess, yeah. The naming is a little bit. There's some rules about that, but that's I don't even want to. The last axis would go towards you. It would go, and I can paint this. I can draw this, but it'll be flawed, of course, because it's really difficult to paint something three-dimensional in 2 dimensions. It's very, well, it's impossible, really. But you can maybe sort of get a sense of the 3rd dimension going towards you. And, well, if you've ever been to the cinema, this is the 3rd dimension they're talking about, isn't it? That the feeling that there's a depth to it. There's a depth to it as well. So yeah, what is a 3-dimensional vector? Well, it's a vector with 3 things told about it. So it's just with 3 slots, and we can start with a nice 3-dimensional vector that we already know. It's this one. Goes 2 in the direction of the x-axis, and this is the point where, when this drawing is reaches its limit. No, just forget the other one, and we'll pretend that this is the x-axis. No. I know. This is turned now, so the x-axis is out here, out towards you, and the y-axis is up, and the z-axis is left. It's very difficult to paint, to draw properly. But then this vector would go 2 in the direction of you. 2 in the direction of you. Outwards, yeah. And it goes 0 in the other 2 directions. So this vector can be viewed as a 1-dimensional vector, a 2-dimensional vector, and a 3-dimensional vector. You can maybe see where this is going, because why only 3? Yeah, a more interesting 3-dimensional vector could be something that actually has a direction in the direction of the other axes. Let's put 5 and 7, and now I should do something I can actually. No, I will not attempt to paint this, but it would go, from the origin, which is the 0 point of all the axes, which is they are on the 0 point of 0 is on top of each other. It would go, somewhere out towards you, but it's a tiny bit difficult to draw. All you need to know is that it goes 7 in the direction of the x-axis, 5 in the direction of the y-axis, and 3 in the dimension of the z-axis. X is first in the alphabet, and therefore it's what we write as the first one as well. It's a nice way to remember. You can of course add 3-dimensional vectors. You can subtract them. It's the same thing. You go. The geometrical interpretation is that you go up 1 vector and goes out the 2nd vector, and then you take the resulting vector from where you started to the place you ended. That's the sum of the 2 vectors, or 3, or however many you want to do. And subtraction, you just go back a vector. You go back in the direction of a vector, and algebraically, it's just first numbers added or subtracted, second numbers added or subtracted, and third numbers added and subtracted. And this you might now notice that there's more options for being orthogonal. For instance, to this vector, there's up here to this vector, there's a few vectors that are orthogonal. There's infinitely many, but there's not that infinitely many. There's all the vectors in this direction. They are orthogonal to this one, and all the vectors in this direction. And that is infinitely many because they can have any length at all. and there's infinitely many lengths that they can have. So there's infinitely many different vectors that are orthogonal to this. But in this three-dimensional case, there's still all the ones going up and all the ones going down, but there's all the ones going to the sides, either side, or to one, to a combination of the two. So they can go, there's sort of a circle of vectors that are all orthogonal to this one, which is quite a few more. As long as they go 0 in the direction of the x-axis there, they will be orthogonal. Yeah. And you can do dot product as well. I don't really know the geometric interpretation of that, but if I had another three-dimensional vector, let's call it 16, 48, and 24, you can take the dot product of these two. This will be take a little while to write, I'm afraid. 17, 5 and 3 multiplied with, but it's the same way that it works. Top ones, middle ones, and the bottom ones multiplied and then added together. Plus 3 times 24, and this will give us 424. Not a clue what this is, what this means. It's just something we can do. And I'm pretty sure if you run into a physicist, he will know. He'll have some case when this is very useful, or he'll have some way of interpreting this. Yeah, because I will try and illustrate. If you had something you can add and take the dot product, and what else can you do? There's orthogonal vectors, yeah. So yeah, these two things, the two-dimensional things and the three-dimensional things, they are very used in physics. Two-dimensional vectors are, for instance, very useful for if you have some ships sailing on an ocean. They'll have some sort of speed. They'll not have speed. They'll have momentum. Is the proper physics for word. They'll have, and if you put down, let's pretend the Earth is flat. Thank you. The ocean is flat, and you can, at least for a smaller area of it, it'll be pretty much flat. You could put down your system of coordinates, and then you can say, well, this boat has a direction, has momentum. And I'll represent that with a direction and a length. So more momentum means a longer vector, and then the direction is very clearly visible, and you can then, and if two boats crash into each other and they have the same weight, the resulting no, this is I'm not a physicist, I can't do examples like that, but oh yeah, I guess if you have your boat, there we are. If you have your boat and it's going in this direction, so this is two-dimensional vector again. Keep making little dots. That's not very nice. I do not like them. And you'd like to change your direction to here. You're going a little bit to this side, and you'd like to go directly. If, for instance, you could be going northeast, and you'd like to go just east. Yeah. you'd like to go just east, you would have to change your momentum. And what you have to change it with is, I have the line, is this. So if you have a certain momentum, yeah, this is because this vector is composed of this vector and this vector, and if you want to take away this vector to make it only just this, you have to add this vector or subtract this vector. It's because this vector is pointing in the other direction. So subtracting this and adding this is the same thing. If you've ever been sailing, or you'll know that adding something in this direction will not matter for how fast you're going in this direction. That's the way this mathematics can help physicists understand the world. Yeah. I will try and show, if you have a ship going in this direction and you'd like it to go in this direction, you have to change it with a force in this direction. So you go that way instead. And this is this is useful for physicists and well, in practical life for sailors, I guess, and people who might do with things who are working in 2 dimensions. But then, of course, if you were flying an airplane instead of sailing a boat, you would you'd need 3 dimensions to describe your place, because you have a height as well over the Earth. Yeah, and for many things like fields and electromagnetic fields, for instance, physicists use 3 dimensions, and they use these operations. The dot product and the addition and subtraction. But as a mathematician, there's no reason this should stop with 3 coordinates. We could go on to 4. Yeah, let's do a 4-dimensional vector, just because. Yeah, it could be the very nice 4-dimensional vector that we have sort of seen before, which is there. And now it comes the point where I can definitely not draw it. I can definitely not. We could take a more interesting one. No, let's just do 1, 1, 1, 1. So it would go from here and 1 out from the screen and 1 in the direction of the Z and the Y axis, and then it would go in 1 in the direction of the fourth axis. And this is I would argue that this is pretty much impossible to imagine, at least spatially. But it's still doable mathematically, because there's nothing that stops us from adding these 2 vectors, for instance. I can do that, no problem. Because these 2 added, can't multiply vectors. This would just make this vector a new vector. Fine. And now I have it loose. I don't have it connected to the real world anymore. This is just in my head, only in my head. Well, not exactly only in my head is this possible, but it's pretty much only possible inside a human head. Yeah. Yeah, there's no... Well, there is one way you could view this 4th coordinate. You could view it as time, actually, because things have a position in time. Yeah. But it gets hairy, let's just say it like that. It's pretty difficult to imagine something in 4 dimensions. And but why would we stop there? We could go to 5 or 6 or 7, and we could keep adding and subtracting and taking dot products, no problem at all. And we could figure out if vectors were orthogonal. Of course, In 4 dimensions, there's again even more vectors orthogonal to this one. Actually, I'd like to do another vector which will look something like this, but not quite. It'll be this vector. This goes nothing in any of these directions, but it goes 3 in the 4th direction. And you could say that it lasts for 3 seconds, if you are inclined towards the time definition. So any vector in this 3-dimensional space will be orthogonal to this one. As long as they go 0 in this direction, they will all be orthogonal. So we started out with, in 1 dimension, nothing is orthogonal, because they are all in the same direction. They are all parallel. Then they can't be orthogonal, of course. In 2 dimensions, there's infinitely up and infinitely down many options. In 3 dimensions, there's infinitely round many orthogonal vectors. But if you have put to a 4-dimensional vector, there's even more orthogonal vectors, and this goes on for, as I said, 5, 6, 7, 8, 9, 10 dimensions, infinite dimensions. That gets a bit more complicated with the whole maths bit, but it's possible. It's called a Hilbert space, I believe. It's if it has infinite dimension. Don't quote me on that, but the mathematicians have been working with infinite, and actually I have been working as well with spaces of infinite dimension, and works fine. 17 dimensions, no problem. And this is it for today. So today you have learned what a vector is, that a number is not just a number can be a vector too. There's 2-dimensional vectors. You can add them, you can subtract them, you can scale them up. I've forgotten to say this, you can scale 3-dimensional and 4-dimensional vectors as well, and nth dimensional vectors as well. It's the same principle of just making them longer. 2-dimensional vectors, and the complex numbers can be viewed as 2-dimensional vectors. With the Pythagorean theorem, we can find the length of 2-dimensional vectors, and I've forgotten to say, but we can do the same for 3-dimensional vectors. It'll be the first the first coordinate squared plus the second coordinate squared plus the third coordinate squared, and the square root of that. Has to be the square root. And you can do the same for 3-dimensional vectors, and 4-dimensional vectors, and 5-dimensional vectors, and 6-dimensional vectors, and 7-dimensional vectors. It's a little bit difficult to imagine, a 500-dimensional vector, but if I wrote it down, I could add 2 500-dimensional vectors together. No problem. No problem at all. I hope your head has been slightly bent, and you've worked your brain out for today.